Hi everybody. In the previous lecture I started explaining column design for pure axial loading. I covered the rectangular and square columns, and the circular columns. Today I'm gonna start explaining the interaction when the column has axial load and bending moment, how we take care of it, and how we use the interaction diagrams to analyze and design these kinds of columns. So there will be an axial and bending moment. That bending moment can be from eccentricity. The load can be eccentric from the center, or the column might be a beam column, which means it has axial load and bending moment. So I'm gonna call it column interaction diagram. So again, in the case when you have pure axial loaded, if we are saying what's the nominal capacity of the column, we are talking about Pn. When we say the design capacity of the column, it's phi Pn. So if it's tight column, the phi factor is 0.65. If it's a spirally reinforced column, meaning the ties are continuous spiral, the phi factor is 0.75. And we gave the equations and we gave example in the previous lecture. Today we have an interaction. Now when we are asked what's the nominal capacity of the column, it's not Pn, it's not Mn, it's a pair. It's Pn, Mn. So if one of them change, the other one will change. So the strength will be the nominal Pn, Mn. There is an interaction between them. And the design, this is the nominal. And the design strength is phi Pn, phi Mn. And this phi factor here, it's 0.65 for both. 0.65 if it's tight column, or 0.75 if it's a spirally reinforced column. Okay, so this is the column that we are talking about. So this is the center of the column, and the load will be applied here at eccentricity. Okay, so we have reinforcement. We have steel in here, and we have steel in here. So this load can be replaced, by the way, by axial load here and bending moment. So axial load and bending, or it can be left this way. So if this is done well, if you take a column to the lab and you load it till the column fail, this is the nominal axial load. And if you multiply that nominal axial load by E, that will give you the nominal Mn. So what's the condition in here? If you what's resisting this one? If I take a cut in here, again, this is equivalent for you to know, this is equivalent to the following. If I move the load here, or replace this with this equivalent system, Mn, and this is the reinforcement. Okay, so what do we have in here? What's resisting? What is the internal resistant of the column? So we will have concrete, could be part of the concrete compression, and part of the concrete will be in tension. Now we could have this steel in tension. Tension in the steel. I'm gonna call this steel, the tension steel, as we use this term for it, AS Fs times stress. This stress could be lower than the tensile, the yield strength of steel. And this steel here is in compression. So I'm gonna call it AS dash Fs dash. Remember, this is not the total AS. This is not the total AS. This is the steel on this side. And you will have the equivalent rectangular area for the concrete. As you know, this is A, and the stress is 0.85 F prime C, right? And remember, this intensity is over the width of the beam. this will give you C from the concrete equal 0.85 F prime C B A, and A equal beta 1C as before in the beam. Beta 1C, and beta 1 equal 0.85 if F prime C is less than 4 KSI, or decrease by 0.05 for every 1 KSI increase in F prime C, as we explained before. So look at this. This is what you may have. At nominal. So if you do sum of the forces in the y direction equal to 0, you will have the following. Pn equal, Pn is down, so anything is up, minus, so Pn equal anything that's up in the y, positive y, minus anything that's in the negative y. So it is 0.85 F prime C BA plus AS dash FS dash minus AS FS. That's the first equation. This is minus. First equation. And sum of the moment must be equal to 0. So in other words, Mn, which is equal to Pne, equal. Mn equal. If we take it about this centroid here. Okay, I will start with the 0.85 F prime C BA. 0.85 F prime C BA. What's the distance from the centroid of this one to the center of the column? Half of the column, this distance from here to here, is h over 2. And this cover here is given, should be given information. Call it d dash on both sides. So the cover is given information. So this distance, the resultant C, is a over 2 from this face. So the distance from the centroid to the center of this C is h over 2 minus a over 2. This is the arm of the compression from the concrete. Okay? And this is balancing this. This is counterclockwise. This is clockwise, this is counterclockwise. So I'm unequal that. Also, let's talk about, so plus AS dash FS dash times the distance from the centroid of AS dash to here, which is h over 2 minus d dash. Now this one is plus, it adds, because it's also counterclockwise. And the sum of the forces in the y direction equal to 0, it was minus. But now it adds, so plus AS FS. What's the distance from this force to the center of the column? The distance from here to here is d minus h over 2. Okay, so this is the second equation. Again, this equation is Pn E. Mn equal Pn E. Okay, so this is the second equation. We have two equations, this and that. If you look at the equation here, by the way, this one, this steel on this side could be in compression. This steel also can be in compression. It depends on the magnitude of the moment. If the moment is small, this will be in compression. If this is in compression, you will calculate Fs negative. So you will, the sign will be taking care of that. So it will be up. It will be resistant. So the calculation, the symmetric triangle, will take care of all these values. Now look how many unknowns we have. We are looking for Pn, and we are looking for Mn, okay, which is usually the eccentricity is given. But usually the eccentricity is given to us. Now A is a function of beta of C, C small. C is the location. C is the location of the neutral axis from the strain distribution. Or I'm going to do it the other way. This is the strain distribution. It looks like that. So this is the location of the tension steel. I'm going to call it epsilon S. This is the location of the compression steel. I'm going to call it epsilon S dash. And this is fixed. This is the ultimate strain, compressive strain in concrete, which is 0.003. This is epsilon ultimate in concrete. This is fixed. So this is C. This is C, small c. Okay, linear. We assume the strain distribution linear. So this is a function of C. Now Fs dash equal epsilon S dash times E of steel. And epsilon S dash can be related to C from the strain distribution. We can find, because this distance from here to here is D, and this is D dash from here to here, so this can be related to C. So Fs dash is a function of C. So, and we can do it. Here. Again, I'm going to clarify the strain distribution, just so you can see it better. So that's this is epsilon S, this is epsilon S dash, and that is 1003, and the distance from here to here is C, and the distance from here to here is D, and this is D dash. As you can see, epsilon S dash over this distance from here to here is C minus D dash. This is C minus D dash. So epsilon S dash over 0.003 equal C minus D dash over C. So epsilon S dash equal 0.003 times C minus D dash over C. Likewise, if you want, epsilon S, okay, over, this is D minus C. So epsilon S over 0.003 equal D minus C over C. So equal 0.003 D minus C over C. So as you can see, if you are analyzing a cross section, it means S is given to you, the cover is given to you, D is given to you, F prime C is given to you, Fy is given to you. So Es dash here is a function of C only, the rest is known. And epsilon S is also a function of C only, the rest is known. It means Fs dash is a function of C, and Fs is a function of C. Okay, and both must be less or equal Fy. If you get it more than Fy, it means it's the steel yield. Both are less or equal Fy. So Fs dash is also a function of C. A is a function of C. Fs is a function of C. As you can see, all can be related to Pn and C. All can be related to Pn and C. So for a given eccentricity E, we can calculate what's Pn and what's Mn. Right? For a given eccentricity, because we have just Pn and C. For a given E, how the load is eccentric or eccentric from the center, we can calculate Pn and Mn and phi Pn and phi Mn from the two equations. But as you can see, it's really not easy. It's not easy. There's a lot of things need to be calculated. A lot of things need to be calculated. Okay? That's why it's always good. That's where it's come the benefit or the advantage of using the interaction diagrams. We can construct an interaction diagram for all these possibilities, for the C value. Now look, there is something called, I'm going to erase this one, I'm going to keep the equations. The balanced condition. The balanced condition. For C balanced. You know what does this mean? This is when epsilon S equal 0.002 at the time when the concrete reached 0.003. So this steel here yields exactly at the same time when the concrete fails. That's the balance condition. For that case, the strength is Pn balance and Mn balance. This is a known point, by the way. This is a known point. Look, C balance, this is here is 0.002. You will have the following. This is, as we said, 0.002, right? And this is 0.003. So this is C. And if I do this similarity between those two triangles, this is 0.002. This is 0.002. And this distance from here is to here is D. So C over D equal 0.003 over 0.005. So C over D equal 0.003 over 0.005 or 3 over 5. This is C balance. This is C balance. So if I know C balance here, I can plug it in this equation. I can calculate Fs dash. I can calculate Fs, which is this Fs will be Fy. This Fs will be Fy. And I can calculate this one, so I can calculate Pn. Okay? Then I can calculate Pn. And then I can calculate Mn. Mn. As you can see, everything is available. That's Mn. This is C. This is C. This is a function of C. This is a function of C. So I can calculate Pn and Mn. For this case, the balance condition. Okay? So that's C balance. Now, the column interaction diagram will look like this. This is, let's say Pn. Let's talk about Pn, the nominal. And this is Mn. Okay? This axis here, if we have zero eccentricity, if E is 0, you are talking about pure axial loading. If there is no axial load, you are talking about the horizontal axis. No loading. So we are talking about this one. So this is a column action. This is a beam action. In between, if there is axial load and there is moment, that's an interaction. That's a beam column behavior. So this one here is the strength if it was pure axial. We knew how to calculate this one from the previous lecture. That's pure axial loading. That's pure axial loading. Okay? That's pure axial loading. It means the eccentricity is 0. We use the equations that we learned the other day. And in this case, this is a beam behavior. This is a beam behavior, which we learned also in beam design. So we know how to get this and that. We know how to get this and that. Okay? We know how to get this one and that. Here again, for this case, P equals 0. So this is equal 0. This one equals 0. You go back to this condition here. Okay? You go back to this condition here, which is doubly. Then you can calculate C. Once you calculate C, you can calculate Mn for this case. Okay? And if there is no bending, it means Mn is 0. So this is 0. So you calculate A from here and go back and calculate Pn. So those can be determined from the equations. And the balanced one, I just showed you how we calculated this one. So usually it is, if this one is here, usually it is somewhere in here. Here it's P balance, Pn of course, and this is M balance. And here this is PO, it means no moment. And this is MO, no axial loading. And the interaction will look like this. Something like that. This is again C balance. This is C balance. Corresponding to C balance is E balance. Okay? If the eccentricity increase, it means the moment increase. If the eccentricity increase, it means the moment increase. If the eccentricity increase, it means C decrease. Why? Because because C is going up, it's shifting up. As the moment increase, C is shifting up. C is decreasing. C is decreasing. It's keep going up. So this steel is in more strain and strain and strain. The strain increase here. So the neutral axis is shifting up. So for again, if E high, C is small. If C is high, E is small. So again, this one corresponds to E balance or C balance, but we'd like to have it with the eccentricity. Okay? So any value that C is more than C balance, it means E is less. It means it's a column action. Any value that's less than E balance, it means C. Any value that's more than E balance, which is less than CB, it is a beam action. Again, so here E is how much? 0. E here is how much? Infinity. So how much C here? Infinity. Means horizontal line or in compression. The concrete is in compression. The case for pure axial loading. So E here is 0, it means C infinity. C here is 0, it means E infinity. And this is C balance, and this is, or E balance, and this value here is, so E is increasing this way. E increasing. Which means C decreasing this way. Okay, so that's the interaction diagram. So once you get, those 3 points are easy to determine from the equation. Once you have C balance, pick a value that's larger than C balance, you get this point, a point here. Pick a value smaller than C balance, which is more than higher E than E balance, you get a point in here, so you can construct the interaction diagram. Or you can put those into Excel sheet and the program will draw all of that. So you just pick values of C from 0 to infinity, to large values. Okay, so that's how we construct the interaction diagram. Now I'm going to show you how we use these interaction diagrams. Remember, this is easy to formulate for rectangular or square, but imagine if you have circular column. Each time you have to calculate the area of that. Thank you, Gerald. Each time you have to calculate the area for that part of the circle, which is not easy to integrate into or to include into the equation. So the interaction diagram will look like this. For a column, given column, the reinforcement is given. Can be 8, can be more than 8, but in this case, the distribution of the steel on the 4 sides is equal. So usually, this is H, okay? This is H, and the distance, this one here is called gamma H. So, in order to see what's gamma, gamma equal H minus 2 times the cover divided by H. So for each interaction diagram, you will see a gamma here. Based on how much H you have and what's the cover, you can calculate gamma. So we have the smallest gamma equal 0.6, then 0.7, 0.8, 0.9. If you have something in between, you do interpolation. And your column that we will do the interaction, it's kind of over that edge. This is the center for Pn over E. Okay, for a given row. So you see the interaction diagrams will look like this. So this is the first one, second one, third, fourth, 5, 6, 7, 8. So this is the first one is for row equal 0.01, which is row minimum, and the last one is for 0.08. Again, this is on the x-axis, the interaction diagram, we have this factor, which is Pn divided by f prime c a gross. So this is not Pn, this is a normalized factor, which is Pn divided by f prime c a gross. And this is Rn, a factor for the moment, which is normalized, which is Pne or Mn. Pne is Mn, guys, divided by f prime c a gross h. Okay, so that's a moment factor. So the first one is 0.01, the last one is 0.08. So your design must be in between that, because this is rho min and rho max. This tip here is the balanced case. So usually those Fs, the stress in the tension steel, equal Fy. Above this, for any row, above this it's a column behavior. Below this one it's more of a beam behavior. So you will see radial lines also. Again, this line here indicate constant eccentricity. What's the eccentricity in here? 0. So this is 0 and this is infinity. So you will have this radial line, the interaction diagram, will tell you E over H equal 0.1. Then you will have another one, and this, and that. So the radial lines are E over H with values. What does this mean? This is the line of constant eccentricity. So if you take a column to the lab and you are loading that column to test and see how much Pn for that column. If you apply at a given E, given eccentricity, okay, and that column has a special rho. Let's say that column has rho equal 0.02. So if you load it from 0, start increasing the load, it will follow the path of that eccentricity, depending on how much eccentricity you apply. Once you reach here, it fails if you have 0.02. If you have more steel, it will fail here. So the more steel you have, the stronger the column for the same cross section. Okay, so these radial lines indicate the path of constant eccentricity. This one for each row. You will see the interaction diagram at certain value here when the moment is small. The moment here, the moment is small in here, and can be ignored. We can consider that case for pure axial loading. You see the interaction diagram has a flat cut in here. There's a flat cut in here. That's the factor that was used for the case of pure axial loading. Remember the tight column multiplied by a factor before that, 0.8, and the spiral reinforced column multiplied by a factor of 0.85. We said in the previous lecture, if you review the previous lecture, these to account for any accidental eccentricity. Though they account for accidental eccentricity. Okay, so this is the interaction diagram for that column. So this is constructed. Can be constructed, as I told you, from the equations using spreadsheets, and people already constructed that, and they look like this. So this is for the case of the steel is all around. This is not a square, it's rectangle and square. So you can have a rectangle with the steel equal on the four sides. That's for gamma equal 0.6, then for gamma equal 0.7, then 0.8, then 0.9, depending on the cover and the dimension of the column, as I told you. Now you go to the second series, when you have something like that, it means the steel is not the same or symmetric on the four sides. So you have to use these things for a square or rectangular column when the distribution of the steel is not the same. Like if you have 6 bars, the distribution will not be the same. If you have 8 bars, it will be the same. 4 bars the same. 12 bars the same. 10 bars not the same. Okay, and again 0.6, 0.7, 0.8, 0.9. Then you start with the circular column, and it's the same case. Okay, just gamma. Okay, just gamma. Okay, so these are the interaction diagram, and this is the cut I told you here. Once you reach here, you see this cut, these horizontal cuts, those to account for accidental eccentricity. So when you design a column using the interaction diagrams or the equations that I covered in the previous lecture, that account for small eccentricity. So if someone's telling you you can't have a column that's pure axial loaded, tell them we take care of that in our equation or in our calculation. The ACI code takes care of that. Okay, So if we want to go over example and see how we use the interaction diagram, I will give you this and I will ask you calculate the nominal strength and the design strength for a given cross section. Take this. For this column, if we have a square column that is 12 inch by 12 inch and it's reinforced with, it's a tight column, the cover is 2 inch to the center of the bars, and those bars are for number 8. Okay, for number 8. What is the design strength for this column? What is the design strength for this column if F prime C equal 4 KSI and Fy equal 60 KSI? Okay, or how much is that? Knowing that this column will have an eccentricity E equal 3 inch. The load will be applied at an eccentricity of 3 inch. It will be applied with eccentricity equal 3 inch. Okay, what's Pn and what's Rn? Okay, as we said, for the interaction diagram, the first thing to use is we need Kn, which is a load factor, normalized load factor, and Rn. And this one is Pn over A gross F prime C, and this one is Mn over A gross H F prime C, or F prime C A gross H. Now what do we have in here? We don't know this one. What if we know what's Kn, we can calculate this one, because whatever we have here is known. A gross equal 12 times 12, and F prime C is 4 KSI. So if I know what's Kn and Rn from the interaction diagram, and I can tell you what's Pn and what's Mn. Okay, in order to get those, I need to go to the interaction diagram. So this is square column, distribution of the steel is equal, cover is 2, so gamma equal H minus 2 times the cover divided by H. H is 12 inch, the cover is 2 inch, so this will be 12 minus 2 times 2 over 12. This is 8 over 12. And that's 8 divided by 12 is 0.667 or 0.67. So gamma equal 0.67. Okay? So the interaction diagram, I have 4.6 and I have 4.7. And 4.667 I need to interpolate. Okay? So this is how I do it. And E is that much. So what's rho for this column? What's rho for this column? Rho equal the area of steel for number 8, which you can pull it easily from the appendix. Okay. So for number of bar 8 to 3.16. 3.16, that's for number 8, they give you area of steel 3.16 divided by 144. So you can get rho equal 2, 2. That's your row. So now you know what's row. The interaction diagram, as I told you, will have this row, and it has this radial line for E over H. In our case, E over H is how much? Equal 3 over 12, which is 0.25. So I have this E over H, and I have rho equal 0.022. You have this intersection. Once you get this intersection, you go horizontal, you get your Kn. You go down, you get your Rn. Again, for this case, we have E and we have H. So E over H is 3 over 12 equal 0.25. And rho equal 0.022. So what you need to do is you need to go to the interaction diagram with 0.6, pull K from there, then go to the interaction diagram with 0.7, get K from there, and do linear interpolation between them. So you will get K for the case of gamma equal 0.667. Once you have that, you have Kn here. You multiply by 144 times 4 to get Pn. Then likewise, go to the 0.6, gamma equal 0.6, get Rn. Then go to the gamma equal 0.7, get Rn. For your case, which is gamma equal 0.667, get Rn from the linear interpolation, then you can get Mn from this one. By multiplying Rn, you will get there A gross H times F prime C. 144, 12 for KSI. With that, you will be able to find the nominal strength, which is a pair, Pn and Mn. This is the nominal strength. So the design strength, for the design, you need to have phi Pn and phi Mn. And since this is tight column, this is 0.65. The phi factor is 0.65 for both. So once you have Pn and Mn for your case, the design strength is phi Pn and phi Mn, which is 0.65 times these values. Okay? And again, this row is good. You have to check, and you know it's more than 0.01 and less than 0.08. And if you want to design the ties, as we said the other day, the size of the tie, if you have number 10 steel and lower, it's number 3. If you have more than number 10, you have number 4. So this is number 8, so this is the tie must be number 3. So what's the spacing of the ties? At what distance we have the ties? The lesser of the 3. 16 times the diameter of the bar. And the diameter of number 10 is 1 inch. So 16 inch. Or 48 times the diameter of the stirrup. And the stirrup is 3/8 of an inch. So 48 divided by 8, that's 6 times 3, that's also 18. So the first one gave us 16, the second one gave us 18. The last one, most of the time, control for small size columns, which is 24 and 12 inch in here, the least dimension of the column. And the least dimension is 12 inch. So this will control. So this is number 3 at 12 inch. Okay? So this is how much this column can resist, and this is how the stirrup should look like once you get these values. I'm going to show you on the interaction diagram for these values, and you can do it on your own. So this, again, interaction diagram for the 0.6, for the 0.6 in here. Okay, so our row was this is the first one is row 0.01, and the second row is 0.02. Our case is 0.022. So the distance between each of them is divided into 5 boxes in here. So you can, to your best, try to locate the 0.022, which is a little bit above 0.02. And E over H, as you can see, 0.1, 0.2, and this is 0.3. So 0.25 is somewhere quarter the distance from here to here. So you can determine where is that with row that you have in here. You go horizontal, you get your Kn, which is to your best. I mean, you can, let's say 0.65 or 0.64 to your best. With a ruler you can have it with a better accuracy. Then the Rn, you go down and you get the value of Rn. Be careful, as I mentioned in the lectures herein, Rn is very sensitive, so try your best to get the actual value for Rn, and if you want to round it little bit below the value that you get, because Rn will be multiplied by large value, which is A gross H and F prime C. So a small difference in Rn give you higher difference in the moment. Just to give you example, if you get your Rn 0.14 or 0.15 and check the difference in the two moments, how much 0.14 will give you and how much 0.15 give you for this column, you may find a difference of about 20 kip foot in the moment. So be careful, try to get Rn to your best and don't round it up, round it little bit lower than the value you have. Okay, so that's an example. In the following lecture, next lecture, I'm gonna have full examples from the book solved on the column interaction diagram. But this is the idea of the column interaction diagram. What's an interaction? It's very important to understand that the strength is no longer Pn, no longer Mn. It's a beam column. There's an interaction between them. There's an interaction between them. Change of one will change the other one. There's an interaction. So a column may fail at 200 kip pure axial, but if you apply like 50 kip foot, that pure axial the axial strength may drop down to 120. So there is an interaction between those. With that, this lecture concludes, and I will see you in the next lecture, which is going to be again example on the column interaction diagrams. See you next time.